Learning objectives. In this chapter, the user will learn the following in detail. Introduction to concept description, data generalization and summarization based characterization, attribute-oriented induction AOI, efficient implementation of AOI, analytical characterization, mining class comparison, discriminating between different classes, mining descriptive measures in large database. Introduction. Data mining can be classified into two categories: descriptive data mining and predictive data mining. Descriptive data mining describes the data set in a concise and summative manner and presents interesting general properties of the data. Moreover, users like the ease and flexibility of having data sets described at different levels of granularity and from different angles. Such descriptive data mining is called concept description and forms an important component of data mining. Predictive data mining analyzes the data in order to construct one or set of models and attempts to predict the behavior of new data sets. Database is usually storing the large amounts of data in great detail. However, users often like to view sets of summarized data in concise, descriptive terms. Such data descriptions may provide an overall picture of a class of data or distinguish it from a set of comparative classes. Introduction to concept description. Concept description. The simplest kind of descriptive data mining is concept description. A concept usually refers to a collection of data, such as frequent buyers, graduate students, and so on. As a data mining task, concept description is not a simple enumeration of the data. Instead, concept description generates descriptions for characterization and comparison of the data. It is sometimes called class description when the concept to be described refers to a class of objects. Characterization provides a concise and succinct summarization of the given collection of the data, while concept or class comparison, also known as discrimination, provides discriminations comparing two or more collections of data. Since concept description involves both characterization and comparison, techniques for accomplishing each of these tasks. Concept description has close ties with data generalization. Given the large amount of data stored in database, it is useful to be able to describe concepts in concise and succinct terms and generalized at multiple levels of abstraction, facilitates users in examining the general behavior of the data. The fundamental difference between concept description in large databases and online analytical processing involve the following. Descriptive versus predictive data mining. Descriptive mining describes concepts or task-relevant data sets in concise, summative, informative, discriminative forms. Predictive mining, based on data and analysis, constructs models for the database and predicts the trend and properties of unknown data. Concept description. Characterization provides a concise and succinct summarization of the given collection of data. Comparison provides descriptions comparing two or more collections of data. Can handle complex data types of the attributes and their aggregations, a more automated process. Analytical characterization. Measures of attribute relevance analysis can be used to help identify irrelevant or weakly relevant attributes that can be excluded from the concept description process. The incorporation of this pre-process step into class characterization or comparison is referred to as analytical characterization or analytical comparison, respectively. The first limitation of class characterization for multidimensional data analysis in data warehouses and OLAP tools is the handling of complex objects. The second limitation is the lack of an automated generalization process. The user must explicitly tell the system which dimension should be included in the class characterization and to how high a level each dimension should be generalized. Actually, the user must specify each step of generalization or specification on any dimension. Even without explicit user instruction, a default value such as 2 to 8 can be set by the data mining system, which would allow each dimension to be generalized to a level that contains only 2 to 8 distinct values. If the user is not satisfied with the current level of generalization, dimensions can be specified on which drill down or roll-up operations should be applied. It is non-trivial for users to determine which dimensions should be included in the analysis of class characteristics. Data relations often contain 50 to 100 attributes, and a user may have little knowledge regarding which attributes or dimensions should be selected for effective data mining. A user may include too few attributes in the analysis, causing the resulting mined description to be incomplete. On the other hand, a user may introduce too many attributes for analysis. Methods should be introduced to perform attribute or dimension relevance analysis in order to filter out statistically irrelevant or weakly relevant attributes and retain or even rank the most relevant attributes for the descriptive mining task at hand. Class characterization that includes the analysis of attribute dimension relevance is called analytical characterization. Class comparison that includes such analysis is called analytical comparison. Intuitively, an attribute or dimension is considered highly relevant with respect to a given class if it is likely that the values of the attribute or dimension may be used to distinguish the class from others. When mining a class comparison or discrimination, the target class and the contrasting classes are explicitly given in the mining query. The relevance analysis should be performed by comparison of these classes, as we shall see below. When mining class characteristics, there is only one class to be characterized. That is, no contrasting class is specified. The contrasting class should be for use in comparable data in the database that excludes a set of data to be characterized. Methods of attribute relevance analysis. The general idea behind attribute relevance analysis is to compute some measure that is used to quantify the relevance of an attribute with respect to a given class or concept. Such measures include information gain, the Gini index, uncertainty, and correlation coefficients. Here we introduce a method that integrates an information gain analysis technique with a dimension-based data analysis method. The resulting method removes the less informative attributes, collecting the more informative ones for use in content description analysis. How does the information gain calculation work? Let phi be a set of training samples where the class label of each sample is known. Each sample is in fact a tuple. One attribute is used to determine the class of the training samples. For instance, the attribute status can be used to define the class label of each sample as either graduate or undergraduate. Suppose that there are m classes. Let S contain Si, samples of class Ci for I equals 1 going up to m. An arbitrary sample belongs to class Ci with probability Si by S, where S is the total number of samples in set S. The expected information needed to classify a given sample is I of S1, S2 to Sm equals minus summation Si by S into log 2 into Si by S. An attribute A with values A1, A2 going up to AV can be used to partition 5 into the subsets Si, Sz going up to Sv, where Sj contains those samples in 5 that have values Aj of A. Let S contain Sy samples of class Q. The expected information based on this partitioning by A is known as the entropy of A. It is the weighted average E of A equals summation j equals 1 to y into I of Sij going up to Smj. The information gain obtained by this partitioning on A is defined by gain of A equals I of S1, S2 going up to Sm minus E of A. In this approach to relevance analysis, we can compute the information gain for each of the attributes defining the samples in S. The attribute with the highest information gain is considered the most discriminating attribute of the given set. By computing the information gain for each attribute, we therefore obtain a ranking of the attributes. This ranking can be used for relevance analysis to select the attributes to be used in concept description. Attribute relevance analysis for concept description is performed as follows. Data collection. Collect data for both the target class and the contrasting class by query processing. For class comparison, the user in the data mining query provides both the target class and the contrasting class. For class characterization, the target class is the class to be characterized, whereas the contrasting class is a set of comparable data that are not in the target class. Preliminary relevance analysis using conservative AOI. This step identifies a set of dimensions and attributes on which the selected relevance measure is to be applied. Since different levels of dimension may have dramatically different relevance with respect to a given class, each attribute defining the conceptual levels of the dimension should be included in the relevance analysis in principle. Attribute-oriented induction AOI can be used to perform some preliminary relevance analysis on the data by removing or generalizing attributes having a very large number of distinct values, such as name and phone numbers. Such attributes are unlikely to be found useful for concept description. To be conservative, the AOI performed here should employ attribute generalization thresholds that are set reasonably large so as to allow more, but not all, attributes to be considered in further relevance analysis by the selected measure. Step 3 below. The relation obtained by such application of AOI is called the candidate relation of the mining task. Remove irrelevant and weakly attributes using the selected relevance analysis measure. Evaluate each attribute in the candidate relation using the selected relevance analysis measure. The relevance measure used in this step may be built into the data mining system or provided by the user. For example, the information gain measured described above may be used. The attributes are then sorted, that is, ranked, according to their computed relevance to the data mining task. Attributes that are not relevant or are weakly relevant to the task are then removed. A threshold may be set to define weakly relevant. This step results in an initial target class working relation and an initial contrasting class working relation. Generate the concept description using AOI. Perform AOI using a less conservative set of attribute generalization thresholds. If the descriptive mining task is class characterization, only the initial target class working relation is included here. If the descriptive mining task is class comparison, both the initial target class working relation and the initial contrasting class working relation are included. The complexity of this procedure is the induction process is performed twice, that is, in preliminary relevance analysis, step 2, and on the initial working relation, step 4. The statistics used in attribute relevance analysis with the selected measure, step 3, may be collected during the scanning of the database in step 2. Data generalization and summarization based characterization. Data generalization by attribute-oriented induction. Data generalization summarizes data by replacing relatively low-level values with higher-level concepts, or by reducing the number of dimensions to summarize data in concept space involving fewer dimensions. Given the large amount of data stored in databases, it is useful to be able to describe concepts in concise and succinct terms at generalized rather than low levels of abstraction. Allowing datasets to be generalized at multiple levels of abstraction facilitates users in examining the general behavior of the data. A concept typically refers to a data collection such as frequent buyers, graduate students, and so on. As a data mining task, concept description is not a simple enumeration of the data. Instead, concept description generates descriptions for data characterization and comparison. It is sometimes called class description when the concept to be described refers to a class of objects. Characterization provides a concise and succinct summarization of the given data collection, while concept or class comparison, also known as discrimination, provides descriptions comparing two or more data collections. Is DataCube technology sufficient to accomplish all kinds of concept description tasks for large datasets? Consider the following cases. Complex data types and aggregation. Data warehouses and OLAP tools are based on a multi-dimensional data model that views data in the form of a data cube consisting of dimensions, attributes, and measures aggregate functions. OLAP systems confine dimensions to non-numeric data and measures to numeric data. The database can include attributes of various data types, which ideally should be included in the concept description. The aggregation of attributes in a database may include sophisticated data types such as a collection of non-numeric data, the merging of spatial regions, the composition of images, the integration of text, and the grouping of object pointers. OLAP, with its restrictions on the possible dimension and measure types, represents a simplified model for data analysis. Concept description should handle complex data types of attributes and their aggregations as necessary. User control versus automation. Online analytical processing in data warehouses is a user-controlled process. The selection of dimensions and the application of OLAP operations are primarily directed and controlled by users. Although the control in most OLAP systems is quite user-friendly, users do require a good understanding of the role of each dimension. In order to find a satisfactory description of the data, users may need to specify a long sequence of OLAP operations. It is often desirable to have a more automated process that helps users determine which dimensions or attributes should be included in the analysis, and the degree to which the given data set should be generalized in order to produce an interesting summarization of the data. Attribute-oriented induction for data characterization. The attribute-oriented induction (AOI) approach to concept description was first proposed in 1989, a few years before the introduction of the data cube approach. The data cube approach is essentially based on materialized views of the data, which typically have been pre-computed in a data warehouse. In general, it performs offline aggregation before an OLAP or data mining query is submitted for processing. On the other hand, the attribute-oriented induction approach is basically a query-oriented, generalization-based online data analysis technique. Note that there is no inherent barrier distinguishing the two approaches based on online aggregation versus offline pre-computation. Some aggregations in the data cube can be computed online, while offline pre-computation of multidimensional space can speed up attribute-oriented induction as well. The general idea of attribute-oriented induction is to first collect the task-relevant data using a database query and then perform generalization based on the examination of the number of each attribute's distinct values in the relevant dataset. The generalization is performed by either attribute removal or attribute generalization. Aggregation is performed by merging identical generalized tuples and accumulating the respective counts. This reduces the size of the generalized dataset. The resulting generalized relation can be mapped into different forms, such as charts or rules, for presentation to the user. First, data focusing should be performed before attribute-oriented induction. This step corresponds to the specification of the task-relevant data, that is, data for analysis. The data are collected based on the information provided in the data mining query. Because a data mining query is usually relevant to only a portion of the database, selecting the relevant dataset not only makes mining more efficient, but also derives more meaningful results than mining the entire database. Specifying the set of relevant attributes may be difficult for the user. A user may select only a few attributes that he or she feels important, while missing others could also play a role in the description. In order to allow generalization on the birthplace dimension, the other attributes defining the dimension should also be included. In other words, having the system automatically include province or state and country as relevant attributes allows city to be generalized to these higher conceptual levels during the induction process. A correlation-based analysis method can be used to perform attribute relevance analysis and filter out statistically irrelevant or weakly relevant attributes from the descriptive mining process. The transform query is executed against the relational database and returns the data. This table is called task-relevant initial working relation. It is the data on which induction will be performed. Note that each tuple is, in fact, a conjunction of attribute value pairs. Hence, we can think of a tuple within a relation as a rule of conjuncts and of induction on the relation as a generalization of these rules. The essential operation of attribute-oriented induction is data generalization, which can be performed in either of two ways on the initial working relation: attribute removal, attribute generalization. Attribute removal. Attribute removal is based on the following rule. If there is a large set of distinct values for an attribute of the initial working relation, but either case 1, there is no generalization operator on the attribute, or case 2, its high-level concepts are expressed in terms of other attributes, then the attribute should be removed from the working relation. An attribute value pair represents a conjunct in a generalized tuple or rule. The removal of a conjunct eliminates a constraint and thus generalizes the rule. If, as in case 1, there is a large set of distinct values for an attribute, but there is no generalization operator for it, the attribute should be removed because it cannot be generalized. Preserving it would imply keeping a large number of disjuncts, which contradicts the goal of generating concise rules. On the other hand, consider case 2, where the attribute's high-level concepts are expressed in terms of other attributes. This rule corresponds to the generalization rule known as dropping condition in the machine learning literature on learning. Attribute generalization. Attribute generalization is based on the following rule. If there is a large set of distinct values for an attribute in the initial working relation, and there exists a set of generalization operators on the attribute, then a generalization operator should be selected and applied to the attribute. Use of a generalization operator to generalize an attribute value within a tuple or rule in the working relation will make the rule cover more of the original data tuples, thus generalizing the concept it represents. This corresponds to the generalization rule known as climbing generalization trees or concept tree ascension. Both rules, attribute removal and attribute generalization, claim that if there is a large set of distinct values for an attribute, further generalization should be applied. Depending on the attributes or application involved, a user may prefer some attributes to remain at a rather low abstraction level, while others are generalized to higher levels. The control of how high an attribute should be generalized is typically quite subjective. The control of this process is called attribute generalization control. If the attribute is generalized too high, it may lead to overgeneralization, and the resulting rules may not be very informative. On the other hand, if the attribute is not generalized to a sufficiently high level, then undergeneralization may result, where the rules obtained may not be informative either. Thus, a balance should be attained in attribute-oriented generalization. There are many possible ways to control a generalization process. Attribute generalization threshold control. The first technique, called attribute generalization threshold control, either sets one generalization threshold for all of the attributes or sets one threshold for each attribute. If the number of distinct values in an attribute is greater than the attribute threshold, further attribute removal or attribute generalization should be performed. Data mining systems typically have a default attribute threshold value, generally ranging from 2 to 8, and should allow experts and users to modify the threshold values as well. If a user feels that the generalization reaches too high a level for a particular attribute, the threshold can be increased. This corresponds to drilling down along the attribute. Also, to further generalize a relation, the user can reduce an attribute threshold, which corresponds to a rolling up along the attribute. Generalized relation threshold control. The second technique, called generalized relation threshold control, sets a threshold for the generalized relation. If the number of distinct tuples in the generalized relation is greater than the threshold, further generalization should be performed. Otherwise, no further generalization should be performed. Such a threshold may also be preset in the data mining system or set by an expert or user and should be adjustable. Otherwise, to further generalize a relation, the threshold can be reduced, which implies rolling up. These two techniques can be applied in sequence. First, apply the attribute threshold control technique to generalize each attribute, and then apply relation threshold control to further reduce the size of the generalized relation. In many database-oriented induction processes, users are interested in obtaining quantitative or statistical information about the data at different abstraction levels. Thus, it is important to accumulate count and other aggregate values in the induction process. Conceptually, this is performed as follows. The aggregate function count is associated with each database tuple. Its value for each tuple in the initial working relation is initialized to 1. Through attribute removal and attribute generalization, tuples within the initial working relation may be generalized, resulting in groups of identical tuples. In this case, all of the identical tuples forming a group should be merged into one tuple. Efficient implementation of attribute-oriented induction. Basic algorithm for attribute-oriented induction. Algorithm. Attribute-oriented induction. Mining generalized characteristics in a relational database given a user's data mining request. Input: DB, a relational database. DB query, a data mining query. A list of attributes containing attributes AI. Gen of AI, a set of concept hierarchies or generalization operators on attributes AI. A gen thresh of AI, attribute generalization thresholds for each AI. Output: P, a prime generalized relation. Method: W gets get task relevant data mining query from database. Let W, the working relation, hold the task relevant data. Prepare for generalization. W. This is implemented as follows. Scan W and collect the distinct values for each attribute. AI. Note, if W is very large, this may be done by examining a sample of W. For each attribute AI, determine whether AI should be removed. If not, compute its minimum desired level Li based on its given or default attribute threshold, and determine the mapping pairs V and V', where V is a distinct value of AI in W, and V' is its corresponding generalized value at level Li. P gets generalization W. The prime generalized relation P is derived by replacing each value V in W by its corresponding V' in the mapping, while accumulating count and computing any other aggregate values. This step can be implemented efficiently using either of the two following variations. For each generalized tuple, insert the tuple into a sorted prime relation P by a binary search. If the tuple is already in P, simply increase its count and other aggregate values accordingly. Otherwise, insert it into P. Since in most cases the number of distinct values at the prime relation level is small, the prime relation can be coded as an m-dimensional array, where m is the number of attributes in P, and each dimension contains the corresponding generalized attribute values. Each array element holds the corresponding count and other aggregation values, if any. The insertion of generalized tuple is performed by measure aggregation in the corresponding array element. The efficiency of this algorithm is analyzed as follows. Step 1 of the algorithm is essentially a relational query to collect the task-relevant data into the working relation W. Its processing efficiency depends on the query processing methods used. Given the successful implementation and commercialization of database systems, this step is expected to have good performance. Step 2. Collect statistics on the working relation. This requires scanning the relation at most once. The cost for computing the minimum desired level and determining the mapping pairs V and V' for each attribute is dependent on the number of distinct values for each attribute and is smaller than W, modulus W, the number of tuples in the working relation. Notice that it may not be necessary to scan the working relation once, since if the working relation is large, a sample of such a relation will be sufficient to get statistics and determine which attribute should be generalized to a certain high level and which attribute should be removed. Moreover, such statistics may also be obtained in the process of extracting and generating a working relation in Step 1. Step 3 derives the prime relation P. This is performed by scanning each tuple in the working relation and inserting generalized tuples into P. There are a total of modulus W tuples in W and P tuples in P. For each tuple T in W, we substitute its attribute values based on the derived mapping pairs. This results in a generalized tuple T1. If variation A is adopted, each T1 takes big O of log P to find the location for the count increment or tuple insertion. Thus, the total time complexity is big O modulus of W into log P for all of the generalized tuples. If variation B is adopted, each T0 takes big O of 1 to find the tuple for the count increment. Thus, the overall time complexity is big O of n for all of the generalized tuples. Mining descriptive measures in large database. We have the aggregate functions like count, sum, average, max, and min in the SQL standards. But we are going to explore the data in a multidimensional manner that we need to take care of the data in several perspectives and represent the data in the much simpler manner than a conventional relational database, since we are going to handle the huge volume of data. So we have measuring the central tendency, measuring the dispersion of data, graph displays of basic statistical class descriptions. Measuring the central tendency. Mean, median, mode, and mid-range are the common central tendencies. Mean with respect to data mining and data warehousing is nothing but the weighted arithmetic mean. The weights reflect the significance, importance, or occurrence frequency attached to the respective values. In this case, we can compute the mean with the frequency values. Median is the middle value in the ordered set, as we all know, and it requires to arrange the distribution in ascending order and applying the formula to calculate the median. Mode is a value that occurs frequently or the value with the highest frequency in the distribution. Empirical relation among mean, median, and mode. Mean minus mode equals 3 times mean minus median. Mid-range is the average of the largest and the smallest values in a set. Measuring the dispersion of data. The degree to which numeric data tend to spread is called the dispersion or variance of the data. The most common measures of dispersion are 5-number summary, interquartile range, standard deviation. Quartiles, outliers, and box plots are used to fragment, cluster, and represent the data respectively. The kth percentile of a set of data in numerical order of the value x having the property that Lk at or below x. Example, in a group of 100 values, the 50th value can be called as 50th percentile. Every 25th percentile value can be called as quartiles. For example, the 25th percentile, 50th percentile, 75th percentile, and 100th percentile are first, second, third, and fourth quartile respectively. Interquartile range is a distance between third and first quartile. Outliers are the values that do not belong to any clusters. The lower bound value is the minimum and the upper bound value is the maximum. The 5-number summary is a representation of minimum value, first quartile value, median, third quartile value, and the maximum value. The box plot is a graphical representation of all the 5 number summary values. Graph displays of basic statistical class descriptions. The data are represented by plotting histograms or frequency histograms. The various representations are quantile plot, histogram, quantile plot, scatter plot, loss curve. Mining class comparison, discriminating between different classes. Class discrimination or comparison, hereafter referred to as class comparison, mines descriptions that distinguish a target class from its contrasting classes. The target and the contrasting classes must be comparable in the sense that they share similar dimensions and attributes. Class comparison procedure. Data collection. The set of relevant data in the database is collected by query processing and is partitioned respectively into a target class and one or a set of contrasting classes. Dimension relevance analysis. If there are many dimensions, then dimension relevance analysis should be performed on these classes to select only the highly relevant dimensions for further analysis. Correlation or entropy-based measures can be used for this step. Synchronized generalization. Generalization is performed on the target class to the level controlled by a user or expert-specified dimension threshold, which results in a prime target class relation. The concepts in the contrasting classes are generalized to the same level as those in the prime target class relation, forming the prime contrasting classes relation. Presentation of the derived comparison. The resulting class comparison description can be visualized in the form of tables, graphs, and rules. This presentation usually includes a contrasting measure such as count percentage count, that reflects the comparison between the target and the contrasting classes. The user can adjust the comparison description by applying drill down, roll up, and other overlap operations to the target and contrasting classes as desired. Example: mining a class comparison. Suppose that you would like to compare the general properties of the graduate and undergraduate students at big university, given the attributes name, gender, major, birthplace, birth date, residence, phone number, and GPA. This data mining task can be expressed in DMQL as shown on screen. First, the query is transformed into 2 relational queries that collect 2 sets of task-relevant data, one for the initial target class working relation and the other for the initial contrasting class working relation, as shown in below tables. This can also be viewed as a construction of a data cube, where the status, graduate or undergraduate, serves as one dimension and the other attributes form the remaining dimension. This table shows the initial working relations, the target class being graduate students. This table shows the initial working relations, the contrasting class being undergraduate students. Second, dimension relevance analysis can be performed when necessary on the 2 classes of data. After this analysis, irrelevant or weakly relevant dimensions, example, name, gender, birthplace, residence, and phone numbers, are removed from the resulting classes. Only the highly relevant attributes are included in the subsequent analysis. Third, synchronous generalization is performed on the target class to the levels controlled by user or expert-specified dimension thresholds, forming the prime target class relation. The contrasting class is generalized to the same levels as those in the prime target class relation, forming the prime contrasting classes relation, as presented in below tables. In comparison with undergraduate students, graduate students tend to be older and have a higher GPA in general. Table shows the prime generalized relation for the target class, graduate students. Table shows prime generalized relation for the contrasting classes, undergraduate students. Finally, the resulting class comparison is presented in the form of tables, graphs, and/or rules. This visualization includes a contrasting measure, example, count percentage, that compares the target class and the contrasting class. Drilling and other overlap operations may be performed on the target and contrasting classes as deemed necessary by the user in order to adjust the abstraction levels of the final description. Conclusion. In this chapter, we have covered the following in detail. Introduction to concept description, data generalization and summarization based characterization, attribute-oriented induction AOI, efficient implementation of AOI, analytical characterization, mining class comparison, discriminating between different classes, mining descriptive measures in large database.